So far we've been dealing with solutions of pure acid or pure base, strong and weak acids, strong and weak bases, and determining the pH of those solutions. Well, it turns out we can also have salts that actually cause a solution to be acidic or basic. And the reason for that is because ions can act as acids or bases. If we consider a nice conjugate acid-base pair here, really obvious. HF is my acid. It donates a hydrogen to produce F-. H3O accepts, H2O accepts the hydrogen to become H3O+, and we can think about these acid-base pairs here. Now, if we think about this reaction in the reverse direction, we have two ions. And if we notice the negative ion, if we wrote out a bunch of these, the negative ion pretty much always serves as a conjugate base, and the positive ion nearly always serves as a conjugate acid. So if you have ions in solution, your positive things tend to either be acidic, or they can also be neutral if they're super weak. Your negative things, your anions, tend to be basic, or again, if they're super weak, they can often be neutral. Now here, we started off with an acid, so we know this is going to be an acidic solution. But we could also put this F- in solution by putting in a salt. Let's say we put in sodium fluoride. Well, we've just seen that F- can serve as a conjugate base. So when this salt breaks apart into Na+ and F-, we're going to have this basic component there. Now, we also have to ask ourselves if this positive component can act as an acid. So salts have cations and anions. They have things that could potentially be acids or bases. So how can we tell which one is which? And the key here is that relationship between conjugate acid-base pairs. The stronger your acid or base, the weaker your conjugate. And at a certain point, if you have a super strong acid, for instance, its conjugate is so weak that it becomes neutral. And we just need to assess when that is. So let's say we had a salt solution and we are trying to determine if it's acidic, basic, or neutral. The very first thing we're going to do is what we just did. So let's use NaF as an example, where we're going to split your salt into a cation and an anion. So this is going to break apart into my Na+ and then my F-. Then what we want to do is turn my cation. We know that cations are going to be conjugate acids. We need to turn it back into a base. And there's two ways we can do that. If we have a metal ion by itself, we're just going to add however many hydroxide groups we need. So here we have a metal ion by itself. So we just add a hydroxide to form NaOH. And we'll look at this second example momentarily. For the anion, it's much simpler. It's always a conjugate base, and to get back to the acid, you just throw an H on that guy. So now I have HF. Now we're going to start with what we've just created and decide if these things are strong, weak, or neutral. And this is just from memorizing, right? We know our strong acids and bases, and if it's not strong, it's weak. We really shouldn't have anything neutral here. I was just putting there for completeness. We're really just worried about if it's strong or weak. So NaOH, that guy is strong. HF, he is a weak acid. Then we need to decide what that means about our original things, the Na and the F-. And what we're going to use is this relationship right here. If you have a really strong acid, for instance, its conjugate is so weak that we can call it neutral. If you had a weak acid, however, its conjugate is also weak. So you always have two weak things paired together, or you have strong and neutral things. So if I had a really strong base, its conjugate would be so weak, I would call it neutral. So we turn strong into neutral, and we turn weak into weak. So for NaOH, NaOH is a strong base. So strong base, his conjugate is going to be neutral. HF is a weak acid, so his conjugate is going to be weak. And then we're just going to compare them. The neutral thing, he's not going to do anything, so I can just cross him out. But the weak thing can act as a weak acid or base. So HF was an acid, that means F- must be a weak base. So NaF is going to be a basic salt. So you just break it apart into your pieces, look at what they come from, decide if they're strong or weak, and then use this relationship to decide if your ions are strong or weak, and then whichever one's stronger wins. And your positive thing is always your acidic component, and your negative thing is always your basic component. Let's look at another example. So let's say I had KCl. So let's break it apart. So we have K plus over here, Cl minus here. I have just a metal ion, so I'm going to give him an OH. Negative one's really easy. I just put an H in front. Now I'm going to decide about these guys. KOH, that's a strong base. HCl, that's a strong acid. Use this relationship right here. Strong means this is a neutral thing. Since KOH is strong, that means this is also a neutral thing. If I have two neutral things, my whole thing's just going to be neutral. So some salts are just neutral. They're not acidic and they're not basic. Both of these are N's. Overall, your guy is going to be neutral. All right, one more example. So let's try NH4ClO. Now, first of all, the tricky thing with this is, where do I split it? With metal ions, it's really easy, but with guys like this, it's not always as clear. So if you see some hydrogens in the middle, go to the last hydrogen and split it there. That's typically going to be the place to go. So I'm going to do NH4, and this side has always got a positive on it, and ClO minus, this guy always has a negative ion. So we split it up. Now we need to turn it into its conjugates. So here's where we go back to this rule about how to turn your cation into its conjugate base. For metal things, we added an OH. We're not going to do that here. If we have only non-metals, we're just going to remove an H plus off the end. So I had NH4, so I'm going to turn this into NH3. ClO minus, still the same rule. We'll turn that into HClO. Okay, so I've turned them back into their pieces. Now I need to decide if they're strong or weak. NH3, that's definitely not a strong base. He's got no hydroxide group in there, so he must be weak. HClO, it's not one of my strong acids, so he must be weak, which means this guy up here is a weak acid. This guy up here is a weak base. Now we've run into trouble. We have two weak things. And so now what we need to do is we need to open up our textbook or our reference sheet or whatever the case may be, and we need to look up the Ka and Kb of these guys, because it will tell us which of these is going to be stronger. So if I look it up, right, these are not memorized, but I look these guys up, I find that the Kb of NH3 is 1.8 times 10 to the negative 5. For HClO, my Ka is 3.50 times 10 to the negative 8. Now, I could do this two ways. One thing is I could use this number and the fact that Ka times Kb is equal to 1.0 times 10 to the negative 14, and I could actually calculate the number for NH4+. But I'm a little lazy. So instead what I'm going to do is remember that relationship, what we have up here. The stronger something is, the weaker its conjugate, and vice versa. So if I look down at this Ka and Kb, I can see that as far as the acid and base, the NH3 has a bigger number, so he's going to be stronger. But that means with the conjugates, it's going to be the exact opposite. So NH3 is stronger than HCO3, or HClO, sorry. NH3 is stronger than HClO, so when we consider their conjugates, NH4 must be weaker than ClO minus. So if it's greater than down here, it's going to be less than up here. So what we're going to do is we're just going to pick the guy who wins. If ClO minus is bigger, that guy's going to win. He's got the stronger component, and so overall, this guy's going to be basic because the weak base component won.